Good morning. Today I am presenting my work titled An Explainable YOLO-based Framework for Brain Tumor Detection in MRI Images. So I myself Akhilay Kumar. I am doing MTech in Artificial Intelligence. Okay, so let's start. So this is the outline of the whole presentation. I'll be covering the following topics in my presentation, which includes the motivation, problem statement, literature review, research gap, dataset, selection, system architecture, methodology, results, conclusion, and future work. So first, let's talk about the motivation of this whole work. So as you can see in the left side diagram, brain tumors are among the most life-threatening diseases, especially the gliomas, which vary in severity. So according to the World Global Statistics, over 322,000 cases were reported in 2022, and the number is increasing. So the early detection is extremely important for the patient survival rate. However, manual MRI analysis is time consuming and it depends heavily on expert radiologists. So the motivation, this motivates the need of an automated AI-based system that can improve the diagnostic accuracy, speed, and consistency while reducing human effort. So in this left side diagram shows the 5-year survival rate of a patient whose disease is diagnosed in the early state, mid state, and the last state. So if its survival rate is around 75% if it's in the first stage, if it's diagnosed in the first stage, and it's very less, the survival rate is very less if it's um, diagnosed in the last stage. So the early detection is very important for survival of a patient. Next, the problem statement. So currently, diagnosing brain tumors manually is time consuming and is very slow, error prone, and it is not scalable. So the existing AI models is very accurate, but it is having three main issues. The first one is it is very slow for real-time applications. The second one is they do not generalize well. That means most of the models are trained on one particular data set, which may be working better with that data set alone. But if we provide an image or some MRI scans from some other data set, the model will fail probably. Then the other issue is most of the models are predicting some output, but it is not telling us why the output was made by the model. So most of the models are like a black box. It doesn't have any explanation. So our goal is to develop a system that is not only fast and accurate and is also explainable for clinical use. Next one is the literature review. The first papers that I have used for this work is the morphological transfer learning based brain tumor detection using YOLO V5, which is published in Multimedia Tools and Application in 2024. So in this paper, they have used a YOLO V5 with the morphological filtering, morphological image processing, dilation, erosion, etc. The data set that they have used is the Bratch 21 dataset uh, with transfer learning for the classification. Then the strength and weaknesses. One of the biggest strength of this paper is that it is having a accuracy of 97.2 for the MAP at 50. And the other one is the lightweight model for real-time use. But the weakness, it has one weakness that it is trained on one single data set, so it does not generalize well on other data set. The second paper that I have used for the study is brain tumor classification based on attention guided deep learning, which was published in Computational Intelligence System in 2022. In this paper, they have designed a dual attention CNN model using RRM optimizer and weight smoothing to boost convergence. The strength of this paper includes very high accuracy, 98.61, better generalization across tumor types. But one of the weaknesses is it is having higher model complexity and slower training. Mm. The third paper that I have referred for this work is brain tumor detection and classification using an optimized CNN, which was published in Diagnostics in 2024. In this paper, they have developed a hyperparameter tuned CNN using stochastic gradient descent and Adam dropout and filter control across three MRI datasets. The strengths of this paper includes balanced accuracy, precision recall, approximately equal to 97.97%, and strong generalization via tuning. The weakness is it needs computational resources and manual hyperparameter tuning. A novel approach for the other paper, the next paper is a novel approach for classifying brain tumor combining SqueezeNet with SVM. It was published in Electronics in 2022. The methodology, they have extracted deep features from lightweight SqueezeNet, then classified using SVM, fine-tuned the network for MRI tumor types. The strengths include low memory footprint, suitable for mobile deployment, good performance there of around 96.5 percentage, but it requires separate feature extraction and SVM tuning. The next paper that we have referred is brain tumor classification using meta heuristics, optimized CNNs, which is published in Journal of Personalized Medicine in 2023. Methodology, CNN optimized using Hawkins optimization, that is HHO, improving feature selection and edge detection in tumor regions. The strength and weakness of this paper includes the accurate and robustness. That is, it's having better accuracy. It is having strong performance on limited data sets. That is one of the weakness, and it requires high training time and optimization cost. So, uh, uh, as we can see from this literature, several approaches have been proposed here. Some works use YOLO-based models with pre-processing techniques, achieving high accuracy and real-time performance. Other works uses attention-based CNNs, which improve accuracy but increase complexity. There are also optimized CNN models and hybrid approaches like SqueezeNet and SVM, which reduces memory usage, but it requires additional tuning. So, overall, most of the models are achieving accuracy above 95%, but they suffer from higher complexity, longer training time, and lack of generalization. Also, we can add this explainable AI thing. So most of these models are not explainable. It is acting as a black box. So the explainability part is also missing in most of the models. Next one is the research gap. From the literature, we identified three main research gap. First one is the scalability. It is not proper. The scalability is not properly analyzed. There is no comparison across different models. Second, most works focuses on classification rather than localization, which is more important in medical diagnosis. And the third one is interpretability. Uh, Interpretability is limited. Many methods rely on gradient-based techniques, which are slower and not suitable for real-time systems. Next one is the dataset description. So for this work, we have used a publicly available Kaggle dataset, Kaggle MRI dataset. The dataset contains 5,249 images divided into 4 classes. glioma, meningioma, pituitary tumor, and no tumor. The dataset is split into 4,737 training images and 512 validation images. All images are annotated using YOLO bounding box. System architecture. This slide shows the overall architecture of the system as shown in the diagram. The input MRI images are passed through multiple YOLO models of different scales. And from each detections, from each of the models performance, we found the best model among all the models. And we found that the YOLO V12N model was the best with the better accuracy and efficiency. So we have selected the YOLO V12N for further experiments. And then the EigenCam is applied on the YOLO V12N model to generate explainability maps highlighting important regions. So the proposed methodology. So our methodology consists of two main components. First one is the YOLO-based detection. We use the YOLO V11 and V12 models with different scales ranging from nano to extra large to analyze the performance versus the efficiency. From our experiments, we found that the YOLO V12N is providing the best balance between accuracy and computational cost. So we have selected that particular model. Second, EigenCam for explainability. So EigenCam is a gradient-free method that extracts feature maps and applies PCA and generates heat maps. These heat maps highlight tumor regions and help in understanding model decision making, making the systems more reliable. So that is the use of the EigenCam to add the explainability into the model. So next is the result analysis. So from the table as shown in the slide, we can see that it is the performance comparison of all the YOLO V11 and V12 models. From this, we can see that the YOLO V12N is performing better as compared to other models in terms of performance and computational cost. Um, the PR curve demonstrates, that is in the next slide. The PR curve is showing a good balance between precision and recall. The PR curve, the qualitative results shows that the model accurately detects tumor and EigenCam highlights the correct regions, confirming the interpretability. So from the figure, we can see that qualitative visualization results of the proposed framework. Each row shows the left side is the original MRI image. The middle one is the YOLO-based tumor detections, and the right one is EigenCam heat map highlighting discriminating regions. Conclusion. So we proposed a scalable YOLO-based framework for brain tumor detection, and we also evaluated multiple model variants and identified YOLO V11N as the optimal model. The system achieves high accuracy while maintaining real-time performance. By integrating the explainable AI that is the EigenCam, we also provide meaningful visual explanations, which improves the clinical trust and usability. Next is the plan for the phase 3. So we plan to develop a web application for real-time usage. We will test the model on unseen dataset for better validation. We also aim to further improve explainability and extend the system for real-world deployment. These are some of the references which we were used in this work. including recent research papers and standard datasets. Thank you.